Welcome to the Minnesota Robotics Institute Colloquium. It's again with distinct pleasure that I'm introducing Professor Catherine Zhao of computer science. She has been one of our top experts in computer vision and machine learning. She has some distinguished work in the broader area with funding from NSF, NIH. She has strong interest in application of these techniques to healthcare. And she's going to talk today about attention in vision-based AI systems. So Catherine, the podium is yours.
Thank you. Thanks a lot, Nikos, for the introduction, and thanks for having me here. It's a great pleasure to be here and share with everyone our works about attention in vision-based AI systems. So I'm Catherine Zhao from Computer Science and Engineering. Here is the outline of today's talk. I'll start with a brief introduction about our research. I'll then talk about attention in computer vision and explainable AI, and also very briefly about our other topics in the lab. And finally, I will show you two examples where we apply our AI techniques in healthcare domains. So this slide illustrates some motivating applications of our research. Very broadly, our goals are designing, developing, and deploying AI techniques that aim to augment and enhance humans. By the way, feel free to interrupt anytime. Would love to have discussions with everyone here anytime, so feel free to do that. And in the last 17, 18 years, the main research fields are computer vision, machine learning, and deep learning. So more specifically in computer vision, we work on core vision problems that include attention, recognition, scene understanding, and so on. We also work on emerging topics that intersect other areas of vision. Other sub-areas of AI, which are getting more and more overlapping with vision and learning and so on, right? As some of you may know. So those topics include reasoning, vision and language, as well as embodied vision. So in machine learning, we develop new learning methods, mostly deep learning methods that aim to address domain-specific issues. And the recent focuses include deep neural network analysis and understanding, aiming to open the black box, and reinforcement learning, as well as learning with scarce or noisy data or labels. We also spend some time working to develop new experimental paradigms that are motivated to collect large-scale, high-quality data that work very well with the deep neural networks. So all these efforts, they integrate successfully to address various applications. Some are highly interdisciplinary, such as understanding and screening mental health, or decoding neural signals that restore hands for amputee patients, and so on. We publish in typical computer vision and machine learning venues, as well as some of the neuroscience and the broader kind of venues. All right, so in this talk, I'll be focusing on attention as an example, introducing our contributions to attention research and leveraging this attention capability for machines in general, AI systems in general, and then followed by two broader applications. So everyone knows attention is. What attention is, right? So here I borrow a working definition from William James, one of the fathers of American psychology. So he said over 100 years ago that apparently we all know attention. It's a key component in our visual system. And this is important. It implies So attention implies a withdrawal from some things in order to deal effectively with others, right? So you probably also have that experience. The input to our retina is just too much, more than our brain can process in real time. So we have to pay attention to decide where we want to attend to and to react in real time, right? Some of you probably have seen demos or those interactive games like the gorilla experiment, where when we're focusing on counting the balls, we totally ignore the changing of the color in the curtains and so on, right? So it's just, attention implements this bottleneck mechanism for us to react in real time. And the same thing for machines nowadays, right? Thanks to all the technological advancement, machines are overwhelmed by their sensory data. So knowing where to look at and to make inferences accordingly are critical to our AI systems for them to answer questions in this example, to navigate, solve problems, and just to interact with the real world with greater autonomy, right? And it also causes all sorts of economic and maybe political interest for people who would like to control our eyeballs, influencing our reasoning and decision making, right? For example, in the advertisement industry. And in general, our work very computational, sometimes involving complicated math. In this talk, I'll try to stay focused on the framework, present some results, just to give a brief picture about what we do. Meanwhile, if you have questions or want me to provide more details, I would be happy to do so too. So this slide sketches the development of attention research. So before 2006, attention research used predominantly synthetic stimuli, and the transition to more naturalistic scenarios were more recent. And in the following, I will be presenting some of our contributions in this transition. So these are mostly our data sets and the new paradigms that we develop and use in attention research. And here illustrates some of our projects, efforts that formulates new problems and developed data sets and paradigms together with new algorithms that address the several challenges in attention research. And we then moved forward, pushed the state of the art by incorporating this attention research to AI systems for them to perform various tasks. So attention serves as an intermediate step rather than the ultimate goal, which decides where to look at. Instead, we know where to look at, we leverage this information, and we use that for an array of different tasks. And further, we also use attention as a interface, a natural interface that help us visualize and improve the black box deep learning process. So in the following, I'll be elaborating 3 projects, those 3 projects starting from our silicon effort. So the silicon project started several years ago, around 2015, and it's an ongoing effort where we try to predict where people look at. So essentially, it solves the task of saliency prediction, or in other words, people say, computational attention models, right? So where attention is like the goal here. And in this effort, I'll also illustrate our contributions in both modeling and data. So on the data end, as some of you know, right, the development of big visual data has progressively pushed the frontier of computer vision. Yet it remained a challenge in attention research, mostly due to the reliance on customized and often expensive eye tracking devices to collect high quality gaze data as ground truths, as labels. And this limits scalability of data. So to solve the scalability issue, we developed a new experimental paradigm that uses general purpose devices like pads or computer mice to collect high quality attention data. And a little bit detail about that. Here we develop a stimuli that encode the visual acuity drop-off as a function of the retina, and we fitted exactly to the retina curve here. And in the experiment, subjects were instructed to move their mouse to where they find interesting. So as you can imagine, this paradigm motivates mouse movement as it reviews what people want to look at in the periphery with high resolution, similar to what we do in daily lives, where we shift our gaze to bring objects of interest to the fovea. And we develop a big data collection and annotation platform that one can use for multiple tasks. And we then thoroughly validate this new experimental paradigm. And for example, we compare it with the high quality eye tracking data from the literature. And we also validate its effectiveness as training data for deep neural networks, as well as a data set for benchmarking those models. And then, you know, since it only requires on the general purpose devices, so we're able to collect a large scale data set with this new method through crowdsourcing. And we collected 1.88 million trials in total. So this makes the largest attention data set, orders of magnitude larger than existing ones since 2015. And it's pretty well received and used by peers from both the industry and academia. So we know that the data set has been used to contribute to products in industry like compression and softwares, for new softwares that is used to redirect user attention, like to remove background distractors in a video conferencing software, and so on. We also host workshops and challenges to promote collaboration from different areas, including vision, attention, and the use of attention data in more general tasks. So our online challenge site has attracted more than 600 submissions so far. So it's been pretty kind of popularly used. On the modeling side, you know, looking wisely and finding the most relevant information from the surroundings is never easy for machines, right? Especially information that comes from all directions, if we think of the immersive scenarios. So conventional models, they tend to detect and focus on those low, those low-level features, local contrast, edges, and so on. Whereas humans would attend to important and relevant semantics. So this is the so-called semantic gap that has been a long-lasting challenge in computational modeling of attention, and underlying this gap, this challenge has been the fundamental, difficulties in machine learning, in machine vision, right? So that is due to the high variability in appearances, the very vast space in tasks and context. So imagine that things that may attract your attention in your daily life may not just due to their categories, but also factors like emotion, density, ambient scene, context, and so on. So here I very briefly illustrate a first deep learning model that addresses this semantic gap. I'm not going to the details, but very briefly, we leverage peripheral vision. We encode the peripheral vision And we design saliency relevant objectives to learn features. We also developed a first fully convolutional architecture for attention that makes use of full mapping information for training here. So for the first time, I can show some experimental results first. So here it compares with the previous record and reports a significant boost in performance over multiple natural scene data sets and with standard matrix. So here you see a big performance jump and making it much closer to the human performance indicated by the red line here. So it sets a milestone, right? Saying that now attention is able to identify semantics rather than a low-level feature. And this has been the gap between previous models and human performance, right? The identification of semantics. And we developed and maintained a live demo online in the last several years, where one can go to the demo site and upload your own image and see how the model predicts where you're going to look at. So the key differentiation feature of this model is its identification of semantics, rather than, for example, the textures or local contrasts in the background. So this model applies pretty reliable for different types of images, different types of scenes, making it a very widely used model in the last several years. And then now we show successes in predicting attention, right? And then the next step is to make use of the attention mechanism and use that to help machines perform a variety of tasks. So this is a very exciting research area. It was not much explored before. And we expect that by analyzing and embedding this attention capability into machines, we could aim for AI systems with both enhanced performance and interpretability. So we first explore the role of attention in an array of computer vision and language tasks. And here I will share with you in the so-called visual question answering task, in short VQA. So some of you may know that in a VQA task, machines are expected to answer open-ended questions while viewing an image or a video. So this is not an easy task for machines. It's a pretty general AI task that requires the understanding of vision, language, as well as knowledge, right? So here I will also illustrate it with immersive scenarios where information comes from all directions. So in those omnidirectional situations. And this mimics the real life embodied scenario. So it expands the naturalistic concept that we've been pushing in the last several years. And for this, we first collect a data set that features attention and answer correctness. So the data set includes a diverse set of both indoor and outdoor videos, as well as questions of different levels of difficulty and different types. Ground truth includes both correct and incorrect answers. This allows the fine-grained analysis modeling of attention and answer correctness, which is a task performance here. And we performed a comprehensive analysis that reveal interesting findings, which demonstrate a strong correlation between attention and task performance. So here, for example, we see that those who answered correctly, answering a question by viewing an image or video, those who answered correctly, they tend to look at task relevant regions. So in this case, the 4 people. However, incorrect answers were from diverse reasons. So for example, in this case, it is because that the most task relevant semantics are grounded in less salient areas. So those participants missed them. And of course, in the real experiment, the details and objects are clearer and bigger, but it's still not easy to find all relevant information due to information overload, right? Information comes from all directions. And secondly, subjective bias may lead to subjective attention. So in this case, some answered car instead of truck without even looking at the back of the vehicle. So they would answer the question with a car instead of a truck. And we also discovered that sometimes attention could be distracted by visually and semantically distracted objects. So in this case, the street lamp looks pretty similar to the flagpole as asked in the question. So those who are distracted by it may not find the correct answer. And finally, timing is also very important. Since the scene is moving, as in our real world situations, looking at the right object at the right time is a critical factor. So in this example, those who missed the train driver as it went by will not be able to find the correct answer. So here I pinpoint certain videos for illustration purposes. The real experiments are long, the videos in those experiments are longer and more complicated. So now we showed that attention plays a role in answering questions. And we propose that we should leverage both incorrect and correct attention for model development. So please note that incorrect attention, areas where one should not look at, but tends to attract attention, was not used in prior works. So no prior works has leveraged such information for model development. And here was the new paradigm and data that highlights the both attention and task performance, the answer correctness. We for the first time able to discover that both types of attention, they help the models learn more discriminative features that are relevant to task success, right? So they're more task relevant, essentially. So a little bit more details. Here, we develop a semantic working memory with attention mechanism that encodes question information and looks for visual semantics over time. And we further design a fine-grained difference loss to learn both correct and incorrect attention jointly. So compared with the conventional method that learns both types of attention separately using their respective data, which is also a probability, also a possibility. Here we find that joint learning them brings advantages, as it forces a network to learn the differences, sometimes pretty subtle, because distractors can be visually or semantically similar to the targets. So this model brings advantages in predicting both correct and incorrect attention, outperforming state-of-the-art models. And further, we found that leveraging both types of attention in other tasks also brings empirical benefits. For example, in this figure, it shows that knowing where to look at, so comparing the first and second bar, it shows that knowing where to look at helps a VQA model to better answer questions, increase its question answering capabilities. And further, comparing the second and third bar, knowing where not to look further increases answer accuracy. And next, I will further elaborate along this line by incorporating attention into machines to support them perform different tasks, as well as visualizing and hopefully improving this, the decision-making process. And as many of you know, in the last decade, computer vision models have achieved significant performance gains due to the big visual data and the complicated, the very powerful deep learning models. Yet, if we try to visualize those different deep learning models, we will find that they're not very good at prioritize visual information for decision making. So for example, here, in order to answer this question, what is a man with a backpack holding? Here are the areas that we visualize a deep learning model look at to generate the answer. So in comparison, if humans are asked the same question, one would probably first select the backpack and then relate the man with the backpack, and then locate the object that the man is holding, and finally query the name of the object in order to answer the original question. So here in this work, I'll show you our preliminary efforts that tries to build in machines the same kind of capability to sequentially look for and make inferences to perform a task. And in this example, to answer a question. So we first develop a new data set that will allow the analysis and modeling of this task. And the new data set features progressive attention and reasoning, as well as answer correctness. And so the data set was made publicly available. In fact, all our data and models are publicly available online. So for those of you who are interested, feel free to take a look. And next, we define a matrix that quantitatively measures whether areas of interest, along the way make sense. So briefly, we decompose a reasoning procedure with a sequence of atomic reasoning operations, such as select, relate, query, and a few others that we defined. And in each reasoning operation, the accuracy is measured by it's essentially based on the semantic meaning of that particular operation, as well as its associated regions. So intuitively, if when one looks at aligns better with the area leading to correct answers, then the score would be higher. So in this case, the area that leading to the correct answer is the area of the cell phone in this particular operation, particular step. And overall, we found that humans who answered correctly tend to attend and reason pretty well, showing high scores along the way. And those who answered incorrectly tend to show dropped scores from a certain step. So in this case, they're distracted by other pedestrians in the scene and missed the one the question asked. And the machines in general show worse scores in general. So now this newly defined matrix, this quantitative matrix, allows more unified studies about a series of questions inside deep neural networks, right? So it helps answer several interesting questions that the deep learning community would be interested in. So there's always a keen interest in understanding more about how it works, why and how the DNN reaches the conclusion as it is. So for example, here we try to answer, do models look at places important to reasoning? and we report the reasonability of different deep neural networks. So overall, we found that existing models, they do not look at relevant places important to reasoning, not as good as humans, even when humans answer incorrectly. And among different deep neural networks, those with object-based attention are better than those with spatial attention. And secondly, we found that machines do not look at the relevant areas to answer correctly. So here in this table, it shows the low correlation between answers and where the models look at. So in fact, some models, they have a very heavy language bias. They depend on this bias in the data set to answer questions rather than observing the visual scene in order to answer questions. So for example, some of you may have heard that in original VQA data set, if you answer tennis to all sport related questions, you probably get accuracy of about 50, right? And if you answer yes to all questions like do you or is there kind of questions, then you get the accuracy of 90%. So this is the so-called language bias that is very, you know, it's something that models heavily depend on, some models, right? So here, our goal is that we hope to develop AI systems that are able to really make use of the visual information in order to make decisions rather than, you know, based on the data set bias, which is not generalizable. And our spatial temporal analysis also revealed that while humans follow pretty much the correct order of reasoning, machines tend to look directly at the final regions of interest, ignoring intermediate steps for decision making. And we then develop a modeling framework where we try to build machines, we guide machines to progressively look and reason in order to reach an answer. So here is an example. To answer this question, what kind of furniture is to the left of the television? A resulting model would first look for and select the television, and then shift its attention to the left and find the furniture on the left and relate that with the television. And finally, query the name of the furniture, which is the bed, in order to answer the question. So in comparison, state-of-the-art models, they do not have this reasoning process, and their attention accuracy is not necessarily accurate. So here we show that our models can outperform others state-of-the-art ones, and equally or more importantly, in my view, are not just this task performance, but also the attention and the reasoning capabilities. So these capabilities are currently lacking in existing models. And having those capabilities would largely increase models' interpretability as well as further performance improvement. Imagine if we have more complicated tasks, or you know, with data set without bias to rely on, right? So those scenarios. And one more thing. So I really want to emphasize that kind of the takeaway message from this this approach or this line of approach, something that really gives us power is the highlight of intermediate steps and the correlation of them with the final task performance. So this allows us to identify key critical factors and visualize them to do a kind of diagnosis and things like that, right? So and our method, as shown here, also provides some quantitative support in you know, in things like explainable AI and so on. So we've demonstrated the usefulness of attention in an array of tasks in the last several years. So here summarizes them. We kind of show that it's useful for classic vision tasks, including recognition, detection, and so on. And language tasks like image captioning, visual question answering, and visual storytelling. So knowing where to look at makes those tasks a lot easier. And we also showed that knowing where to look at attention helps machines to show emotions. So there's a couple works that we can analyze attention and image sentiment and so on. And beyond interpretability and performance, we also demonstrate that knowing where to look at requires less data for training and alleviates adversarial examples. So it's just like, what we have, this attention system in humans and the primates, right? So this is a very inherent capability that would be helpful in many ways. It's a very fundamental function of the visual system. And I know some of you may have wondered, right, if our brain has unlimited power, unlimited bandwidth, do we still need that? And the answer is yes, right? So imagine that if we process everywhere, it's more like we're treating the targets and distractors the same way. And there would, it's not very good for the task, the ultimate task, right? In contrast, attention helps us distinguish tasks that are relevant, targets that are relevant to the task from distractors, therefore boosting performance, boosting interpretability, as well as, making it more robust to adversarial attacks and so on. So this is more about attention that I try to wrap up in the last slide. And we're also working on some other tasks that are very exciting. I don't have time, but here are some brief kind of illustration of them. So here I pick a theme in the previous slides about attention, which is pretty consistent, right? But we're also heavily working on these areas as well. So for example, we're focusing on reasoning with knowledge. And this aims to improve deep learning models' generalizability. So deep learning models would not only rely on the data they've seen, but also able to infer with common sense or other types of external knowledge. And we also work on embodied vision problems, where to develop embodied agents, vision and action needs to be tightly coupled. And over the last several years, we've also paying good attention to explainable and trustworthy AI. So this line of research aims to open the black box nature of deep learning models and to ensure a safe and effective use of those models. And finally, we also develop some machine learning methods that address the main specific challenges. Mostly in the visual domain with images and videos, as well as in the healthcare domain, as I will be introducing later on. So are there any questions so far before I move on to talk about the two examples in the healthcare domain in the next 10-15 minutes? All right, maybe we can put the questions toward the end. So I always hold a very strong belief that technology is about humans. So we want to develop, advance and deploy technologies to help people in need. And here are two examples along this direction. First, AI in mental health. So mental disorders have been the most costly conditions in the United States since 2016. And it's also very prevalent. Yet there's not yet a critical mass that AI brings to help mental health screening or treatment. Current diagnosis pretty much requires specialized clinicians and relies on questionnaires and interviews. So they can be subjective and sometimes inconsistent. It's also episodic, and cost and convenience are other factors that limit the amount and quality of professional input. And so there is a critical need in mental health screening that helps keep track, understand, and treat disorders when needed. And here we're seeking AI's help to provide a solution that complements and improves the existing one, and in democratizing and also making it accessible to different parts of the global population. And in the last 10 years, I work with the domain experts, the clinicians. We together work on methods that understand and screen neurodevelopmental and psychiatric disorders. So briefly, our methods are pretty well received from multiple domains. There have been discussions in the scientific community and the reports in media that speak high of our methods, and some discuss its prospect of revolutionizing mental health screening. So here is an overview. Here illustrates some of the projects that we carried out in the last several years for the goal of understanding and screening mental health. Very briefly, we leveraged our advancement in the computational field with the new data and models. So for example, we conduct new experiments with autism subjects using our new naturalistic data set. And we then further conducted a new experiments that allow subjects to work in open immersive environment while recording their attention preference. So you can imagine that compared with the standard practice where a happy or a sad or an emotional face is shown at the center of the screen, our paradigm, these new ones are they're more ecologically relevant, and the visual input in that scenario is, it includes a much wider range of semantics and features. And then our data-driven deep learning methods successfully characterized these much more complicated high-dimensional data, leading to new and exciting discoveries, some of which were not hypothesized in the community. So this is kind of really the power of deep learning, data-driven kind of approach. And we also further developed several screening methods focusing on interpretability to kind of review neurobehavioral signatures and achieve breakthroughs in autism screening. And in the last few years, we've been expanding some of those core methods into a few directions. First, we're focusing on the heterogeneity, where the heterogeneity both within one disorder as well as with the multiple of them, right? Some mental disorders, they co-occur, for example. So this aims for personalized treatment. And we also study the longitudinal dimension with the developmental populations from toddlers. And with the new mouse tracking paradigm, we're collecting more data, we're offering much increased accessibility and scalability to to the multiple clinical populations. So it's being used in multiple labs and clinics, allowing large-scale research and screening. And I would like to conclude the talk with our recent progress in another collaboration in a brain-machine interface, where my collaborators, neural engineers, physiologists, and surgeons, they developed a medical grade implantation system, the physiology and surgical techniques to implant the system into human nerves. And the role of my lab is to decode neuron signals to restore hands for amputee patients, for them to control robotic hand and to play video games. So here in this video, it shows part of the complicated surgical procedure where our collaborator is implanting electrodes into an ulnar nerve of a subject. So electrodes are very, very tiny. So those electrodes are, they stay in the subjects, and the data that we analyze are recorded from those electrodes. So far we've done those chronic human trials with 6 patients, and accumulated implantation time is over 15,000 hours. So most of it is done at UMN here. So this generates, very exciting data, biggest human nerve data that could potentially benefit millions of people, right? But the data comes with some prices. Something that's advertised as science fiction movies as decoding intention is not as trivial. So those data come with many challenges, for example, like the dynamic nature, inherent plasticity of neuron data. And those data are highly complicated. Signal from one electrode could be combined activities of hundreds of individual axons. Signal to noise ratio could be low because those insulating layers making signals weak. And there are many sources of noises, such as interference of residual muscles, motion, and so on, just to name a couple. And further, the human trials are very expensive. So this makes the data pretty scarce, both labels and data scarce compared with the typical conventional computer vision or other applications. And there's also requirement of online low latency decoding of AI algorithms. So it comes with a bunch of challenges that were not addressed in the deep learning or computer vision literature. So if we take off-the-shelf models, they simply don't work at all. And over the last several years, we've been working to address those challenges. And we developed deep recurrent neural networks with attention mechanism to learn neuron features and to decode neural signals, to decode the motor intention. So when the neuron data that reflect human intention and the deep neural network that we know are pretty powerful in deriving new things, right? When they meet, it's actually a very exciting opportunity. And I would like to highlight 2 highlights so far. So first, in the literature of upper limb prosthesis, the ultimate goal for research and essentially the ultimate goal of that community is to realize individual, at will control of individual fingers, right? So, so this is quite a few degrees of freedom. And the current practice, however, is that you know, algorithms are able to pre-program several patterns, commonly used patterns like grasp patterns or other commonly used ones, pre-programmed, and the subject would activate one at a time. So it's not individual finger movement that realize that intuitive control of hands. And in our case, we achieved individual joint movement with 15 degrees of freedom. So we, in our paradigm, we allow each finger to freely move. I mean, in each joint. So it's at will, very intuitive at will control. And this is much higher degrees than existing methods that we can find in the literature. So the second thing that I want to mention, as an AI researcher, I feel it's really exciting to see the procedure that's happening here, where we can observe that while machines, they tune themselves, they tune, they refine attention and tune their performance with better and more data. Humans, they also adapt, right? They also learn and adapt to better express their intention, to mind control the prosthetic hands, right? So in a way, this realizes a human-machine bidirectional mutual learning and adaptation. So this is kind of a true integration of artificial intelligence and human intelligence. And here is a video showing the decoding results. So on the left hand are the neural signals, and on the left are the decoded results. So it realizes this individual finger movement, which was not demonstrated elsewhere.
No.
Okay, so I'm going to move the pinky finger first. I'm going to move the index. I'm going to move the middle finger. I'm going to move the ring finger. Now I'm going to move the thumb. Now I'm going to make a fist.
And here's another video of a short conversation with a subject. So this subject has been wearing prosthesis for 7 years. He's a pretty experienced user. And for the first time, he is able to control the robotic hand at free will with individual finger movement.
Do you have truly independent finger control, not like the grasp patterns that are programmed into your...
Absolutely. This is nothing like a grasp pattern. This is, I think with training for myself and then learning models like this, I can get back to a natural hand movement.
Is it pleasurable playing with it?
Oh yeah.
Okay.
It's just really cool.
Okay.
Like this is crazy cool.
And here is the same subject playing video games. So please note that there's no connection between the subject and the computer. So he's mind controlling the helicopter in the game. And when the subject was asked about the most exciting applications of this technique, he said games. And he also expressed that the experience to control things in a computer is pretty unique and very cool. And I would like to conclude this talk. This is the final slide by a Turing test, where you see two hands. So the subject is playing mirrored hand movement. So one hand is recorded, the real hand is recorded by a data graph, and the other is by AI decoding. So please, try to differentiate which is the real hand and which is AI hand. All right, any guesses?
They're very similar in any case.
That's right. Yeah, I'm not able to tell either. So here, this one is a real hand, and the right one is AI hand. And the fact that they're really similar says that AI is really cool here, right? And I would like to thank all my students and collaborators who made this talk possible. And finally, thank you for your attention.
Thank you.
Thank you, Catherine. So questions?
I have a question about the robotics hand.
Yeah, sure.
How do you ensure that, is it generalizable, or basically the signals are for one person that you train the neural network?
That's a great question. We do have to train with each person, and there's definitely, we're working on hopefully better models that could, require, could require less data or fine-tuning time for new patients, right? But on the other hand, training that for each individual person is more like a personal prescription for that particular person to better support their individual kind of life, or better cater their individual kind of neuron characteristics and so on. Yeah, so yes, the answer is we do need to train it with individual ones, at least so far.
Thank you.
With respect to all of these demonstrations at the end with the robotic hand and then the video game, how much of a gap is there between the response speed and tracking when it's a human actuated one versus when it's, so like someone who doesn't have a, that doesn't need a prosthetic device versus something like this? Is there like a large gap, or do you see a future where maybe a prosthetic would be even faster than a human hand, or video game reaction speed, right?
That's a great question. Yeah, so for now, I believe that the latency that we achieved here is much faster than what the community has, which the BCI community usually has a latency in the order of second, like 1 to second. And what we had the last time I heard was about 0.2 seconds also. And that includes the time that the signal was transmitted from the brain to the hand, right, to the arm. And, the time that the algorithm runs, which I believe is minimum. That's probably the easiest part. I don't want to take credit from, other team members, but, and the time that we need to transmit it, the hardware kind of time, right? So, and to your other question, whether, it can be faster than the real human, that's a great question that I haven't thought about. Yeah, I'm not sure about that. Because,
Sure.
you know, the hardware team is has been kind of trying hard to reduce latency from, you know, the transmission time, dealing with those hardwares and so on. So that part, I'm not sure how to kind of, you know, reduce or even, you know, try to eliminate that latency. Yeah, I'm not an expert there, so
Mhm.
I
All
don't
right,
know
thank
what
you.
the limit is. Sure, that's a great question.
Hi, Professor. I had another question.
Sure.
It was on your work about using correct and incorrect attention for training the models.
Mhm.
I was just curious how you actually get labeled data for incorrect attention. How was that?
That's a very good question. That's a very good question. So normally we don't have that data in a traditional data set, right? And just for that purpose, I mean, not just for that purpose, but partly because of that we create a new data set that we had provided the grounded truth, incorrect answers. So some answered incorrectly, and we annotate them, and we also have the corresponding areas that, you know, the areas that they look that lead to those incorrect answers. So we use that as a ground truth for as incorrect attention.
Okay, got it. Thanks, Professor.
Sure.
Other questions? So Catherine, thank you very much. We really appreciate the presentation.
Thank you. Thank you, everyone.
So-
Thanks, Nikos.
Stay well, everybody, and have a great weekend.